The boom and bust nature of epidemics is a central part of popular culture, as featured in numerous blockbuster movies and best-selling paperbacks. Epidemics are scary and fascinating at the same time. The more explosive and gory, the more scary and fascinating. In real life, only a subset of infectious diseases causes epidemics, and only a subset of those again exhibit the truly explosive kind that scares and fascinates. Epidemiological theory helps us understand when epidemics may happen and what pathogen features are associated with epidemics. Epidemics are most commonly associated with acute, highly transmissible, directly transmitted pathogens that either kills its host or induce strong protective immunity. As we will discuss shortly, these traits are associated with both the initial explosive spread and the subsequent self-limitation and end of the epidemic. To understand the epidemic curve caused by such pathogen, we use a stylized so-called SIR compartmental framework. The acronym is short for susceptible, infected, removed. The idea is that we can think of a host population to be comprised of individuals that can be classified as either susceptible, infected and infectious, or removed from the chain of the infection. The removal can be either because an infected individual dies of disease or because an infected individual recovers and becomes immune to reinfection. Smallpox and many vaccine-preventable childhood infections like measles, mumps and rubella adheres to this description. According to the SIR caricature of the epidemic, we assume that everybody meets at random so that infectious, susceptible and immune are equally likely to mix socially. The epidemic starts when an infectious individual enters a population of susceptible individuals. This will spark off a chain of transmission and an initially exponential increase in the number of cases. The exact speed of increase depends on the reproductive number R0 and the infectious period. The higher the R0 and the shorter the infectious period, the more explosive is the spread. With a flu-like infection with an R0 of just under 2 and an infectious period of 2 to 3 days, the epidemic doubles every 3 days or so. This rapid doubling happens because early on in the epidemic, almost all individuals are susceptible, and almost all potentially contagious contacts lead to new infections. However, the initial exponential increase in infected individuals also lead to an exponential decrease in the number of susceptible individuals. As the susceptible pool is depleted and infectious and removed individuals are becoming more numerous, an increasing fraction of contacts does not lead to new infections. These are dead-end contacts from the point of view of the pathogen. We call the average number of new infections later in the epidemic the effective reproductive number, RE, to distinguish it from the basic reproductive number. The effective reproductive number is equal to R0 multiplied by the fraction of the population that is still susceptible. Once RE falls below 1, the epidemic becomes self-limiting. On average, each new infected individual will fail to infect another person before being removed, and the epidemic loses momentum. The exact time at which self-limitation outweighs contagion is when the proportion of susceptible in the population fall below 1 divided by R0. This is the point at which we say the population is reaching herd immunity. Thereafter, the epidemic slowly grinds to a halt, and in the case of our stylized epidemic curve, is predicted to leave a fraction, which in mathematical terms is predicted to be equal to the anti-log of the negative R0, untouched. The graph shows the predicted final epidemic size as a function of R0. The pace of the epidemic is influenced by the duration of infectious period and also the latent period, the time it takes from being infected to becoming infectious. Influenza, for example, is a very acute infection with a short infectious period. The seasonal flu epidemic, consequently, typically becomes self-limiting after a month or two, and the epidemic typically self-extinguishes some weeks thereafter. Tuberculosis, in contrast, has a variable but very long, sometimes decades-long latent period. and sometimes lifelong infectious period thereafter. As a consequence, its epidemics are slower to spread, but also extremely slow to self-limit. The global TB epidemic that was recognized as a global emergency by WHO in 1993 is still, 30 years later, growing by more than 8 million new cases each year. In fact, at the current pace of spread, there is no sign of self-limitation, as the global susceptible population is replenished through births as fast as it's being depleted through infection. This letter is in fact an important additional insight. We only expect boom and bust epidemics if transmission is fast relative to demographic turnover in the host population. If the two processes are comparable in speed, we expect prevalence to reach an endemic steady state. This situation may in both demographic and economic terms be more harmful and costly than the explosive and gory epidemic that scares and fascinates us so.